Hello and welcome to the AICE Chemistry lecture series. In this video we're going to cover chapter 8.6, which we're going to focus on the acid-base equilibrium. So we're going to grab what we talked about equilibriums in the first part of this chapter, and we're going to apply it specifically to acids and bases and their reactions. Now, in order to do this, we first need to have a very thorough conversations about what acids are, what bases are, and how do we measure their strengths. So let's start with this. The first thing we ever learn about acids and bases in our science education is the pH scale. We know that the pH scale helps us figure out if things are acidic or basic by which number from 1 to 14 a specific solution has. Acids have a pH range below 7, whereas bases have a pH range above 7. And anything that is exactly 7 is considered to be a neutral solution, which is neither an acid nor a base. The pH scale was introduced by a Danish chemist named Søren Sørensen in order to avoid dealing with a wide range of hydrogen ion concentrations in solution. We already saw this in earlier chapters, but the pH scale is based on pH, which is equal to the negative log of the hydrogen ion concentration of a solution. Meaning that the higher the concentration of hydrogen ions, because it's a negative log, the higher this number is, the lower the pH. That's why acids have a pH range below 7, because acids have a high hydrogen ion concentration. That relationship between the hydrogen ion concentration and the pH comes from this negative in the equation. Now, this is an equation you should already be familiar with from honors chemistry. And if you're not, you need to remember it, because it is an equation that we're going to use a lot, and that helps us understand the relationship between the hydrogen ion concentration and the pH. Now, here are the pHs of some common compounds and some common everyday life chemicals. Hydrochloric acid at 1 molar concentration has a pH of 0. It has a really high hydrogen ion concentration, which gives it a really low pH. Things like lemon juice and vinegar, which we know to be acidic, have pHs of 2.3 and 3.0. Coffee, rainwater, which might come as a surprise to you, saliva are all acidic compounds with a pH lower than 7. On the other side, things that are basic are things like seawater with a pH of around 8.5, above 7, milk of magnesia, water with soap in it, and even sodium hydroxide, which has a pH of 14 when it's 1 molar. So you can see that these have a much higher pH when they're bases, meaning that their pH is high because the hydrogen ion concentration is low. So the hydrogen ion concentration and the pH have an inverse relationship. Hydrogen ion concentration goes up, pH goes down because of the negative in the equation. Let's keep going. So acids and bases, when they react with each other, undergo a neutralization reaction when the base is an alkali. And this is a very important point to make here as we get into a more in-depth conversation about acids and bases. An alkali is a water-soluble base. So the same base and alkali is not necessarily the same. All alkalis are bases, but not all bases are alkalis, because not all bases are water-soluble. So an alkali is specifically a base that dissolves in water. Now, when a base that dissolves in water, an alkali, reacts with an acid, we get what is called a neutralization reaction. That acid reacts with the alkali to create water and a salt. The ionic equation that happens here is that hydrogen ions react with hydroxide ions to create water. The salt, the ionic compound that is made from this reaction, will depend on what our acid and base are. So a few things to point out here. Salt. What is a salt? A salt is an ionic compound. And this is going to be made from the cation of the base and the anion of the acid. Why is the reaction H plus plus OH minus for the ionic equation for the neutralization reaction? Well, one thing that all acids will have is a hydrogen ion. And we'll see this in the next slide, or the next couple of slides, so the definition of an acid. But all acids will start with hydrogen, meaning they have a hydrogen ion. Alkalis, water-soluble bases, not all bases, but alkalis specifically, have hydroxide ions in them. They're ionic compounds with hydroxide ions. So in any neutralization reaction, the hydrogen and hydroxide ion are always present, and they are going to come together, H plus and OH minus, to create H2O. It's a little easier to see if we write H2O as HOH, which is still H2O, 2 hydrogens, 1 oxygen. But you can see how hydrogen and hydroxide can come together to create HOH, or water, H2O. This is going to happen in every neutralization reaction. So here are some examples of that, right? We have sulfuric acid reacted with sodium hydroxide. Sulfuric acid has a hydrogen ion, it's an acid. Sodium hydroxide has a hydroxide ion, being a base, an alkali specifically, because it has dissolving water. So sodium hydroxide and hydrochloric acid, sulfuric acid are going to react with each other to create water, because it always makes water neutralization reaction, and sodium sulfate. Why sodium sulfate? Sodium sulfate comes from the fact that the anion in the acid is a sulfate ion, and sodium is the cation in the base, sodium hydroxide. The sodium Na2SO4 is going to come from the fact that the sodium ion is Na+, whereas the SO4 ion is SO4 2-. When we cross these, we get a 2-to-1 ratio of Na2SO4. And that's where the sodium sulfate comes from. That is what we call the salt, the ionic compound created by this neutralization reaction. Similarly, we have hydrochloric acid, HCl, that chlorine there being the anion, and barium hydroxide, with the barium being the cation. The hydrogen from the hydrochloric acid and the hydroxide from the alkali from the barium hydroxide create the water, again, which is present in all neutralization reactions. And then the barium and the chlorine come together to create the barium chloride. Barium is a 2+ cation, chlorine is a Cl-1 anion. So when we cross them, we get a 1-to-2 ratio of BaCl2, which is the ionic compound made, or the salt made in this neutralization reaction. So these are some examples of neutralization reactions. Neutralization reactions are always going to make that water that we discussed, and they're always going to make an ionic compound created from the anion of the acid and the cation of the base. And they always create water because acids always have hydrogen ions and alkalis always have hydroxide ions. Not all bases do, again, but alkalis, specifically water-soluble bases, do. So let's keep going and talk about what exactly is an acid and what exactly is a base. So let's start with a simple definition of an acid, because there are actually many different definitions of acids and bases. There are, depending on the theory you're working with, I think there are 4 in total, 4 different definitions of acids and bases. We are only going to work with 2 of those 4 because that's what's in the curriculum, but also makes our lives a lot easier. The simplest practical definition of an acid, the one that we have been working with since honors chemistry, is a substance that releases hydrogen ions when dissolved in water. Meaning that anytime you dissolve an acid in water, you'll get H+, a hydrogen ion. All right. Hydrogen ions will always react with water to create hydronium ions. Whenever we have H+ in water, H+ is the hydrogen ion, which is essentially just a proton. Remember that hydrogen ion, if it's hydrogen 1, has 1 proton, 1 proton and 1 electron, 0 neutrons. If we remove that electron to be H+, that means the hydrogen ion is just a proton. Well, a proton is going to attach to anything that is even mildly negative. Water, being a polar molecule, has a partially negative oxygen. So that hydrogen ion when it meets a water molecule, so if we draw a water molecule here, when that hydrogen ion, which is essentially just a proton, meets that water molecule, it's going to be attracted to that partial negative oxygen in the water molecule. That partial negative oxygen in the water molecule is going to use its lone pair of electrons to pick up that hydrogen ion and create a dative covalent bond, creating what we know as the hydronium ion, H3O+, which is just oxygen with 3 hydrogens attached to it. One of them through a dative covalent bond, which is the one that was just picked up here, and it has a lone pair of electrons. Now, because it has that extra hydrogen, it gets the hydrogen's ions +1 charge. So that's a +1 ion. So the hydronium ion and hydrogen ions are really the same thing. We can use either of these 2 modes of showing hydrogen ions. We can write as H plus aqueous, or we can write as H3O plus aqueous, because anytime hydrogen ions are in water, they're automatically going to attach to the water to create hydronium. So the hydronium ion is a more accurate way of showing it, but sometimes hydrogen ions, just being shown as H plus, can make visualizing a lot easier. So both of these are used interchangeably. Now, we do still need to make sure that we have a balance in a reaction that we draw. So whenever we write the dissociation of an acid, we can do so in 2 ways. So what is dissociation? Remember, dissociation when it comes to ionic compounds is the ionic compound separating into its individual ions in water. Well, dissociation when it comes to acids, because they're not ionic compounds, is the ionization, meaning they get turned into ions of an acid or a base into the ions in the presence of water. So dissociation is essentially the same thing as it is for ionic compounds. It's a separation of the acid or a base into ions in water, but it is the ionization, not just separation, because ionic acids are not ionic compounds. They are covalent compounds, and so they get ionized. They get turned into ions. They're just separating into ions. It's all just, semantics and vocabulary, but it's important for you to know. So like I was saying, we can write the dissociation of an acid in water in 2 ways, because we can either write it with H plus or with hydronium, H3O plus. The first way will be to write an acid. We'll take hydrochloric acid, which is a very simple acid as an example. We'll take the acid and write it as reacting with aqueous with a lot of water. And so that acid is just going to split up into H plus and Cl minus. Another way to write this is just HCl aqueous instead of HCl gas plus aqueous. So it'll just be to write HCl aqueous yields H plus aqueous plus Cl minus aqueous. So in this manner, we're showing the dissociation of the acid as just the acid splitting into hydrogen ions and the anion in the aqueous form. The more accurate way of doing this is as a reaction, writing the HCl, the hydrochloric acid, reacting with water molecules, and where the water molecules pick up the hydrogen to create the hydronium ion, H3O plus aqueous, plus the Cl minus aqueous, then anion. So we can write this in either way. They're both correct technically, but notice how we need that water in the reactant side here to make sure that that H3O plus makes sense. Otherwise, we wouldn't be able, if you just throw H3O plus and HCl on this side, where did that oxygen come from, right? So we need a water molecule. Whereas when we're writing it as a dissociation, just splitting into the hydrogen ion and the anion, we don't put the water in the reactant side, because then we'll need to put the oxygen somewhere here. So that's the simple definition of an acid. It is a compound that releases hydrogen ions when dissolved in water. Hydrogen ions can also be written as hydronium ions anytime there is water around. And we can write their dissociation in 2 ways, either without the water to create just the hydrogen ion and the anion, or with the water to create the hydronium ion and the anion. Now let's discuss bases, which are a little simpler. what is the simple definition of a base? Again, there are many different definitions of acids and bases. Again, I think there are 4 in total, but there might be more. The simplest practical definition of a base is a substance that releases hydroxide ions when dissolved in water. So a base is not going to release hydrogen ions like acids, they're going to release hydroxide ions. Oops, right, a bracket there. It's hydroxide ions in water. Hydroxide ions react with hydrogen ions in the water to lower their concentration. So one of the things that we said about pH is that bases are going to have a high pH because their hydrogen ion concentration is low. Well, why does that happen? Why is the hydrogen ion concentration of our base low and its pH high if they don't have hydrogen ions? Well, hydrogen ions in water, already present in water, can react with hydroxide ions that are released by the base, and they create water. So by the base releasing hydroxides, what it's doing is that it's reacting those hydroxides with the hydrogen ions in the water, because even pure water has hydrogen ions, and it creates water molecules. By doing this, it lowers the concentration of the hydrogen ion. So most all alkalis and a lot of bases contain hydroxide ions directly, like sodium hydroxide, which is an alkali, contains hydroxide ions directly, and we can write the dissociation as the alkali separating into the sodium ions, in this case, or what are the cation is, and the hydroxide ions. However, not all bases have hydroxide in them. Ammonia, for example, is a base. Some bases, instead of creating hydroxide by dissociating and releasing the hydroxide, are going to create hydroxide by the reaction with water. Ammonia is an example of this. Ammonia reacts with water and steals a hydrogen from that water, creating the hydroxide ion. So bases like ammonia, bases that do not contain hydroxide, create hydroxide by stealing a hydrogen from the water molecules, creating, in this case, what we call hydronium, NH4+, although it does depend on the base, and then therefore creating hydroxide ion, because what is water without that hydrogen? It's simply just a hydroxide ion. So that water molecule, just like before with the hydronium, that water can have one of its hydrogens stolen by something like ammonia. So we'll draw ammonia here. And that water can, essentially, or that ammonia can use its lone pair to steal a hydrogen from the water. These electrons go back to that water. And so what we end up with is the ammonium ion, which is simply just, let me put this in blue. It's going to create ammonium, which is just ammonia with its 3 original hydrogens. But now also the hydrogen that is stole from the water, red, with a +1 charge because of the hydrogen that is stole. And then the hydroxide ion, which I'm going to draw here in yellow, which is just the water with the OH with that extra lone pair of electrons from the bond breaking, which is going to give it a negative charge. And that's a hydroxide ion. So while some bases directly donate or create the hydroxide by dissociating, some of them created that hydroxide by stealing hydrogens from water, creating some kind of cation, and then the hydroxide ion. So those are the basic definitions of acid and base. Acids create hydrogen ions when dissolved in water. Bases create hydroxide ions when dissolved in water. A more inclusive definition of acids and bases is what we call the Brønsted-Lowry theory of acids and bases. In the Brønsted-Lowry theory of acids and bases, neutralization reactions are based on the transfer of a proton. Like I said earlier, a proton is essentially just a hydrogen ion, right? Because if you take an electron from hydrogen 1, since it doesn't have any neutrons, it's just going to be a floating proton. So Brønsted-Lowry theory bases neutralization reactions on whether something donates a proton, it's giving up a proton, or something picks up a proton, it's accepting it. A Brønsted-Lowry acid is essentially a proton donor. Again, proton being H+, so it is a H+ donor, something that gives up hydrogen ions. And a Brønsted-Lowry base is a proton or a H+ acceptor, something that uses a lone pair of electrons to pick up a hydrogen ion. So the acid must have a removable hydrogen to create the hydrogen ion or the proton. All Brønsted-Lowry acids have a hydrogen on a polar bond, which makes them easier to remove. So, for example, if we look at hydrogen chloride, very simple acid, HCl. If we look at HCl, HCl is a polar molecule where the hydrogen is partially positive and the chlorine is partially negative. Because HCl has a hydrogen on a polar bond, it acts like an acid. And it does so because this hydrogen here is removable. Because it's on a polar bond, it's easier to remove since the electrons are already closer to the chlorine. And so it can easily donate, become a proton donor. It can donate that hydrogen to an acid in a neutralization reaction. On the other hand, during the transfer of electrons in a neutralization reaction, the bases have to have a lone pair of electrons to create the dative covalent bond with the hydrogen ion that we saw earlier. When I write the example for the water with ammonia. So because bases have to use a lone pair to create a dative covalent bond with the hydrogen ions, all Brønsted-Lowry bases have to have a lone pair of electrons somewhere on them. So we can look at a neutralization reaction, for example, between hydrogen chloride, HCl, and water, where water acts like a base. In this reaction, we have the water and the HCl reacting to create hydronium and chlorine. So let's look at what that looks like in a closer look. So here we have HCl reacting with water. So HCl is going to act like our acid here. And the water is going to act like our base. And we'll talk about why water can act as a base in a little bit. But water reacts with hydrochloric acid, HCl, to create two things. So that create hydronium. Ooh, that got really big. So that create hydronium ions, H3O plus, and the chloride ions, Cl minus. So you might have noticed this is the dissociation of hydrochloric acid. Well, in the Brønsted-Lowry theory of acids and bases, the dissociation of an acid is an acid-base reaction. It's a neutralization reaction between an acid and water, which is acting like a base. So what is going on here? If we draw the HCl, so HCl is going to be chlorine bonded to hydrogen, with the chlorine having 3 lone pairs of electrons. And then if we draw the water, which is an oxygen with hydrogen, another hydrogen, and 2 lone pairs of electrons. So here water can act like a base because it has lone pair of electrons that it can use to make dative covalent bonds. On the other hand, HCl is an acid because it has a removable hydrogen, because the hydrogen here is partially positive and the chlorine is partially negative, meaning this is a polar bond with a hydrogen on it. What's going to happen here is that the base, which has lone pairs of electrons, it's going to use one of those lone pairs of electrons to create a dative covalent bond to the hydrogen. So it's going to steal the hydrogen away from the rest of the acid. The hydrogen-chlorine bond, or the hydrogen bond, the polar bond the hydrogen is on, is going to break with the electrons going to that other compound. And so when this happens, we create two things. We first create the hydronium ion, or in this case, well, we create whatever the base is going to create with an extra hydrogen, in this case, a hydronium ion, where you have the water as it originally was, but it has now used one of its lone pair of electrons to pick up a hydrogen ion from the acid. So that hydrogen ion came from the acid. And then we also are going to have the chlorine, Cl, with its three original pairs of lone pairs of electrons, but it also has that extra lone pair gained from the bond breaking, making it a negative ion, or the chloride ion. So you can see that in this reaction, we have, and let me change the color of this yield arrow in the center just so we can make it easier to visualize. So what we have here is that during this reaction, the base, the water, picks up a hydrogen. So it's a hydrogen acceptor, a proton acceptor, creating that new compound. And then the acid is a proton donor. It's donating or giving up the hydrogen to the base, creating our whatever that acid is without the hydrogen. Notice also the charges. Hydrogens carry an innate positive charge, and I actually forgot a charge here. This hydronium ion is +1 because it's gaining a hydrogen ion, it's gaining a proton. And the chloride is -1 because it's losing that proton, it's losing the hydrogen ion. So this is what is essentially happening in a Brønsted-Lowry acid-base reaction, where the acid acts like a proton donor and the base acts like a proton acceptor. The base is using its lone pair of electrons to pick up the hydrogen from the acid and therefore breaking the polar bond where the hydrogen is on the acid. All right, let's go back to the PowerPoint. So that is the Brønsted-Lowry theory of acids and bases. Now that we discussed the definition of both acids and bases when it comes to the Brønsted-Lowry theory, let's discuss what amphoteric substances are. The most common example of an amphoteric substance is water. Amphoteric substances are essentially just substances that can act both as acids and bases. They're substances that have both a removable hydrogen, so they can act like a base, like an acid, and they have lone pairs, so they can act like a base in the Brønsted-Lowry theory. So for example, in the reaction we just saw, water was acting like a base, where it used its lone pair of electrons to pick up the proton from hydrochloric acid. So in this example, let me use a different color. In this example, water is acting like a base. However, water also has removable protons. In water, the hydrogens are partially positive, whereas the oxygens are partially negative. Because the hydrogens in water are partially positive and the oxygens are partially negative, we have a polar bond where the hydrogen is removable. Because of this, water can also act like an acid. Like in that reaction we saw earlier with ammonia, where ammonia uses lone pair to remove a hydrogen from water. In that particular case, water was acting like an acid. So because water can both act like an acid and as a base, depending on what it's paired up with, we say water is amphoteric, because it can be both an acid and a base. It has both lone pairs of electrons and removable protons. So just a piece of vocabulary you need to be aware of, amphoteric. Brønsted-Lowry theory is going to give us a broader scope to how we react or how we look at acids and bases. It is more inclusive of compounds as being acids or bases because it does not require the presence of water. Unlike the basic definition where hydrogen ions and hydroxide ions were created in water, the Brønsted-Lowry definition defining acids as proton donors and bases as proton acceptors makes this a more inclusive theory. As long as they meet those criteria, they can be acids and bases even if water is not present. This is particularly true when we look at organic compounds, or when we look at acids and bases and reactions with weak acids and bases, and we'll discuss what that means in a little bit, but reactions where the water is not present and instead it's two different compounds reacting with each other, often in equilibrium reactions. So for example, perchloric acid, HClO4, can react with what we call ethanoic acid, and I know it sounds rare because it's supposed to be an acid, but ethanoic acid can be amphoteric as well. So perchloric acid can react with ethanoic acid, where the perchloric acid loses the hydrogen and gives it to the ethanoic acid, gives ClO4 minus, and then the ethanoic acid becomes CH3COH2 plus 1. So we essentially add an extra hydrogen to this oxygen here at the end. In this sense, the ethanoic acid is acting amphoterically. It is picking up a hydrogen, becoming a base, acting like a base. And it creates these two compounds. But because that ethanoic acid, as the name implies, is amphoteric, doesn't want to necessarily pick up a hydrogen, this becomes an equilibrium reaction. But notice, there's no water present anywhere in this reaction. So acid-base reactions in the Brønsted-Lowry theory can happen where water is not present. So let's talk about this. Why does this form an equilibrium, and what exactly is a weak acid and a weak base? There are two classifications of acids and bases. The first is strong. So a strong acid are those which are going to completely dissociate into their ions when exposed to water. So acids and bases can both be categorized into either weak or strong, depending on how much they dissociate. A strong acid dissociates completely. For example, hydrochloric acid is a strong acid. Hydrochloric acid, when it reacts with water, all of the hydrochloric acid molecules will give up their hydrogen to become Cl-, and all of the hydrogens are going to be given to water molecules, becoming hydronium ions. This is a full dissociation, or a complete dissociation. There is no back and forth, there's no equilibrium. Every single one of the HCl molecules dissociates and becomes Cl-, making hydrochloric acid a strong acid, because we have complete dissociation. So strong acids are associated with complete dissociation when they're exposed to water. So strong acids completely dissociate. On the other hand, a weak acid is going to be an acid where it only partially dissociates into their ions. A weak acid does not completely dissociate. It only partially dissociates when exposed to water. So these acids react with water and form an equilibrium reaction with the water instead of a complete dissociation like hydrochloric acid. So that ethanoic acid we saw earlier was a weak acid. When it reacts with water, when it's acting like an acid and reacts with water, some of those ethanoic acid molecules give the hydrogen to the water to become hydronium. But some of them stay as ethanoic acid instead of losing that hydrogen and becoming what we call the ethanoate ion here. So because they don't completely dissociate, they create an equilibrium where in that solution you have both the completed ethanoic acid molecule and hydronium ions as well as the ethanoate ion, all in the mixture. So how do we know if an acid is a weak acid or a strong acid, if it completely dissociates or if it partially dissociates? Well, there are only 7 strong acids in chemistry. Depending on who you ask, might be 6, but in your curriculum it's 7. So there are only 7 strong acids in chemistry, and they're listed right here. We have nitric acid, HNO3, perchloric acid, HClO4, chloric acid, HClO3, sulfuric acid, H2SO4. Only the first deprotonation, and we'll talk about what this means in a little bit in the next slide actually. Hydrochloric acid, HCl, hydrobromic acid, HBr, and hydroiodic acid, HI. These are the 7 strong acids, meaning that if something is an acid, like ethanoic acid, CH3COH, but it's not one of these 7, it's automatically weak. So what do we need to do? We need to memorize these 7 strong acids. You need to memorize them so that you know if you see one of these, it's a strong acid, and if it's an acid that's not one of these, it's a weak acid. Meaning these are the only 7 acids that are going to completely dissociate when reacted with water, whereas all the weak acids, which is any other acid that's not these, will only partially dissociate, creating an equilibrium. And because of that, we get all these interactions between strong and weak acids, where strong acids have a much higher concentration of hydronium ions or hydrogen ions, and weak acids have a much lower one because of the equilibrium nature of the dissociation. Meaning the pH of a strong acid will be much higher, the pH of a weak acid will be, much lower, should I say. It will be much lower, and then the pH of a weak acid will be much higher because it will not be as low as that of a strong acid. Polyprotic acids. Now, polyprotic acids are a special subsection of acids like sulfuric acid, for example. Some acids have more than one removable hydrogen. There are acids that have more than one hydrogen that is polar and can be removed on the molecule. We call those polyprotic acids. Poly being multiple, protic being hydrogen or proton. So polyprotic with multiple protons. Each dissociation of a hydrogen for polyprotic acid, though, is seen as a separate reaction with its own strength. Sulfuric acid is a perfect example of this. When sulfuric acid dissociates, it actually dissociates in 2 steps. First, the sulfuric acid H2SO4 has 2 hydrogens that are removable, reacts with water, and it gets rid of only one of those acids, or hydrogens, sorry. It only gets rid of one of those hydrogens. So H2SO4 gets rid of one hydrogen with one water, creates hydronium, H3O+, and the HSO4 minus ion. So notice how it only got rid of one of those 2 hydrogens to create HSO4 minus. The second dissociation of sulfuric acid is when that HSO4 that was created then gets rid of its one hydrogen with water to create the hydronium ion and the sulfate ion, SO4 2 minus. So those 2 hydrogens in sulfuric acid don't get removed at the same time. They get removed sequentially, first one, then the other. Because of it, we get 2 dissociations for sulfuric acid. Like I said earlier, sulfuric acid is considered to be a strong acid. It's right here, but only its first dissociation. The losing of the first hydrogen by sulfuric acid is a strong, complete dissociation. It is what makes it a strong acid. But losing that second acid by HSO4 minus is a equilibrium reaction. It is a partial dissociation, meaning that it is a weak acid or a weak dissociation. So we say sulfuric acid, H2SO4, is a strong acid, but HSO4 minus ions are a weak acid because that is the second dissociation, which is separate from the first. So that's what polyprotic acids do. Most polyprotic acids though have 2 or 3 even weak dissociations. Some compounds can even create acids when they react with water. Carbon dioxide, for example, reacts with water to create carbonic acid. Even though carbon dioxide itself is not an acid, when it reacts with water, it does create an acid, which is the carbonic acid H2CO3. This is why carbon dioxide in the atmosphere, excess carbon dioxide in the atmosphere, can cause acidification of things like the ocean and lakes and rivers, because excess carbon dioxide can dissolve in that water to create carbonic acid. Very common example, or very common theme that you study in AS Marine Science, for example, or A-Level Marine Science. The first dissociation of carbonic acid is weak, as is the second, but there are 2 dissociations. Carbonic acid is a polyprotic acid. The first dissociation is when the carbonic acid loses one hydrogen to water, creating hydronium and the HCO3 minus ion. And the second dissociation is when that HCO3 minus ion reacts with the water again to create a hydronium and the carbonate ion CO3 2 minus. So this is 2 examples of polyprotic acids. Only sulfuric acid is strong, has a strong first dissociation because sulfuric acid is the only polyprotic strong acid. Carbonic acid, any other polyprotic acid, it has multiple weak dissociations, although there are different extents to how weak they are. But that is something we're going to study in A-level chemistry. So let's switch over to the same definitions, but for bases. Base strength. Bases may be also categorized as either weak or strong, and it essentially boils down to the same thing. Strong bases are those which are going to completely dissociate into hydroxide ions. As such, they all contain hydroxide ions in them. So strong bases are water-soluble compounds that are hydroxides. So essentially, they're water-soluble or alkalis that have hydroxide in them. Sodium hydroxide is an example of this. When sodium hydroxide is placed in water, sodium hydroxide is extremely soluble in water, so it all dissociates into sodium ions and hydroxide ions. So any water-soluble alkali, any water-soluble hydroxide compound is going to be a strong base. So essentially what this means is water-soluble hydroxide compounds, ionic compounds. Now there are no covalent hydroxide compounds, but just to be more specific, water-soluble hydroxide ionic compounds. So what are the water-soluble hydroxide ionic compounds? What are strong bases going to be? They are group 1, and I have it right here. Let me erase that. They're going to be group 1 and heavy group 2 hydroxides. So all strong bases are either hydroxides of a group 1 element or a heavy group 2 element. Actually, let me do this one in different colors so I can show you here. Or a heavy group 2 element. What do we mean by heavy group 2 element? We mean on the periodic table sodium or calcium and below. So calcium hydroxide is a strong base, strontium hydroxide, barium hydroxide, and radon hydroxide, all of which are group 2 elements. The main ones missing here are magnesium and beryllium hydroxide. And then group 1 hydroxides are any group 1 element hydroxide. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and francium hydroxide. So these are group 1, these are heavy group 2. Magnesium hydroxide and beryllium hydroxide are not strong bases. And the reason why is that they're not water soluble. Remember, according to the solubility rules we learn in honors chemistry, not every ionic compound will dissolve completely in water. And as such, not every hydroxide is a strong base. For example, aluminum hydroxide is not a strong base. Iron hydroxide, copper 1 hydroxide, they're not strong bases because they're not necessarily water soluble or highly water soluble. Weak bases are those which form equilibrium reactions with water to create hydroxide ions. So there are really two kind of subsections of weak bases. There's those that are just not water soluble hydroxides. They only dissolve a little bit in water. And then there's the covalent compounds like ammonia, which react with water, creating an equilibrium reaction where hydroxide is made. Ammonia can react with water in an acid-base reaction, in a dissociation reaction, to create ammonium and hydroxide ions. But this is an equilibrium because ammonia is a weak base. And so any covalent compound that is a base, most of which will include some form of nitrogen in them, are going to be weak bases. Essentially, if you see nitrogen in a compound that is covalent, that is a very good indication that it is a weak base. Nitrogen is one of the main elements that is associated with weak bases that are covalently bonded. So these are the base strengths. If it's one of these, it's a strong base. So if it's a group 1 hydroxide or a heavy group 2 hydroxide, calcium and below, it's a strong base. And if not one of these, then it's going to be a weak base, usually something with nitrogen in it, a covalent compound with nitrogen in it. So how does this strength difference, the weak versus the strong, affect the pH of solutions of these acids, right? How can we tell if something's strong or weak? Well, the pH is a pretty good indication. We can distinguish the strength of an acid or a base from their pH in equimolar solutions. So a solution of a strong base will have a much lower pH when compared to that of a weak acid whenever we have an equimolar solution. So let me rephrase that. Strong acids will have a much lower pH than weak acids when we're comparing equimolar solutions. What is an equimolar solution? Equi means the same. Molar means molarity or concentration. Equimolar solutions are solutions that have the same concentration. So we can see that right here, for example. When we compare the concentration, the pH of a hydrochloric acid solution versus an ethanoic acid solution. If we compare the pH of a 1 mole per cubic decimeter solution of each of those, pH of the hydrochloric acid, which is a strong acid, is 0, whereas the pH of the ethanoic acid, which is a weak acid, is 2.4 when it's a 1 mole per cubic decimeter solution. Now, because pH is a result of the concentration of hydrogen ions, because remember that pH is equal to negative log of the hydrogen ion concentration, that means concentrations of the solutions do matter. If we instead look at a 0.1 mole per cubic decimeter solution, the pH of a hydrochloric acid solution at that concentration is 1 versus the ethanoic acid is 2.9. Still, hydrochloric acid is going to be lower than the ethanoic acid because they're equimolar solutions that have the same concentration. And then if we do a 0.01 molar solution, then we're looking at a pH of 2 for hydrochloric acid versus 3.4 for ethanoic acid. So again, hydrochloric acid is going to be lower. The strong acid has a lower pH than the weak acid if they're equimolar solutions. We cannot compare non-equimolar solutions because if you notice, even though hydrochloric acid is a strong acid and the ethanoic acid is a weak acid, if we compare the 0.01 molar hydrochloric acid solution to the 1 molar ethanoic acid solution, the 1 molar ethanoic acid solution has almost the same pH because these two are not equimolar to each other, they don't have the same concentration. Again, concentration does affect pH, and so we can only use this idea of a strong acid having a lower pH than a weak acid if the solutions are equimolar. Now, pH is a measurement of the concentration of hydrogen ions. The lower the pH value, the higher the concentration of the hydrogen ions, which is why strong acids are going to have lower pHs. Because a strong acid dissociates more completely, and so a strong acid will have a much higher concentration of hydrogen ions than an equimolar solution of a weak acid. Because in the weak acid, not every single molecule is being converted to hydrogen ions, whereas in the strong acid, every single molecule is being converted to hydrogen ions. And it's the opposite, right? It's an inverse for a base. A strong base will have a much higher pH than a weak base of equimolar solution. So an equimolar solution of 1 mole per cubic decimeter of sodium hydroxide has a pH of 14, where ammonia, which is a weak base, has 11.6, right? It is much lower, much lower. Why lower? Because remember, the higher the pH, the less hydrogen ions we have. A strong base is going to release a lot more hydroxide, meaning it's going to get rid of a lot more hydrogen, making that pH spike up. All right. So we can look at the pH. Strong acids have a lower pHs than weak acids. Strong bases have much higher pHs than weak bases. Again, as long as they're equimolar. So how do we measure pH? How can we measure the pH of a solution? Well, there are two ways of measuring the pH of a solution. The first way of measuring the pH of a solution is by using what we call a pH probe or electrode, pH electrode. This is what pH probe is up here in red with a red outline. It is essentially an electronic tool that is going to use electric currents to measure the concentration of hydrogen ions. Now, how can it do this? Well, The strength of the acid and the pH and the total amount of hydrogen ion concentration can affect the electrical conductivity of a solution. The more hydrogen ions there are, the more free electrons the more free ions or charged particles we have, so the more it conducts electricity. We'll discuss that in the next slide. But for now, just know that a pH probe or pH electrode uses electrical currents to measure the concentration of hydrogen ions. And we have a little computer system attached to that probe that can read the exact readout of the electrical current and do some math and transform it to a pH. So pH probes are completely electronic and use electrical currents to measure pH, and they're very exact. On the other hand, we can also use universal indicator paper. Universal indicator paper is essentially a piece of paper that has been soaked in a special mixture of chemicals that change color based on pH. The paper will turn different colors according to what pH the solution that it was dipped into has. So, for example, in this one right here, in the green outline, you can see that at 0 pH has a very deep red color, and then it moves its way through orange, yellow, green, blue, and then a really dark blue-black as the pH goes up. So you dip this paper into your solution, depending on what color it changes, it gives you an idea of the range of the pH that the solution has. This method does not give a specific pH, but a range, so you can do it around 13 and around 10. Not exactly 13.2 or 10.1 or anything like that. It's not an exact measurement. So depending on what you need to use it for, you might use pH paper or universal indicator paper, or you might use a measuring of pH probe instead if you need more accurate data. So this is how we measure the pH. The pH being different for a weak acid versus a strong acid, and the same for bases, is based on their properties. So acids will have, and we're not going to focus so much on the properties of bases because it's not in your curriculum, but acids have different properties based on whether they're strong or weak. The greater the concentration of hydrogen ions, which is going to be present in the strong acid, is going to account for two main properties that are stronger for a strong acid than a weak one. First of all, strong acid solutions are going to have a higher electrical conductivity than an equimolar solution of the weak acid. And we talked about this in a little bit in the last slide. A strong acid has a higher electrical conductivity than a weak acid. The reason for this is the complete dissociation of the ions. Because the acid completely dissociate, there's a higher number of free hydrogen ions or free ions floating around. Ions that are mobile, ions that can move around, are what give ionic compounds and acids their electrical conductivity. Because a strong acid is going to have a higher concentration or a higher number of hydrogen ions floating around, it has a higher electrical conductivity, which is what that pH probe uses to figure out the pH of the solution. Also, strong acids are going to react more vigorously with active metals. So they react more vigorously with active metals. First of all, what is an active metal? Because that's probably the first thing that you are wondering. Well, active metals are just really reactive metals, which are usually group 1 and 2 metals. So alkali metals and the alkaline earth metals are reactive metals because they just generally react very strongly with acids, bases, and with chemicals in general. So group 1 or 2 metals are what we call active metals, the representative metals, if you will. Strong acids are going to react more vigorously with them because the reaction of active metals with acids is actually a reaction of the hydrogen ion. The higher concentration of hydrogen ions for a strong acid is going to speed up the reaction between the metal and the acid. And it's going to give us a faster release of hydrogen gas. That's what we mean by a more vigorously. More vigorous means it happens faster, we get more gas at a time. For example, let's look at the reaction of magnesium with hydrochloric acid, which is a strong acid. Magnesium reacts with hydrochloric acid in a 1:2 ratio to create magnesium chloride and hydrogen gas. In reality, what this reaction is in the net ionic equation, the chlorine is actually a spectator ion. The net ionic equation, is just magnesium solid, it's a single replacement reaction, reacting with two hydrogen ions in their aqueous form from the acid, not the chlorine is a spectator, to create the magnesium 2+ ion, because this is a redox reaction, like we saw in the last chapter, and H2 gas. So this is both a single replacement reaction and a redox reaction, where the hydrogen ions gain electrons to go from a +1 to a 0 oxidation number, meaning that they get reduced. And magnesium goes from being magnesium solid with a 0 oxidation number to magnesium 2+, meaning magnesium is getting oxidized. So it's a redox reaction. So the higher the concentration of the hydrogen ion here, the more quickly this reaction will happen. Because hydrogen ion is one of the main ions in this reaction, the more hydrogen ion we have, the more quickly this reaction happens. Meaning that a strong acid, which has a much higher concentration of hydrogen ions, is going to undergo this reaction a lot more quickly, giving you more gas per second. And that's why a strong acid like this one, believe this is hydrochloric acid, is going to react with this magnesium metal a lot more quickly than a weak acid like this one. And so we got a more vigorous reaction with a strong acid. So that's the two properties of acids that you need to know of weak versus strong. Strong acids have a higher electrical conductivity because of their higher number of dissociated hydrogen ions, which give more free-floating ions, which means more electrical conductivity. And strong acids are also going to react more vigorously with active metals, which are group 1 and 2 metals. And so this is because the concentration of hydrogen ions is much higher, making the reaction move a lot faster. Because hydrogen ions are one of the two reactants when we write the net ionic equation for this reaction. Now, before we start looking at some questions from the AICE exam, let's look a little bit at vocabulary. Because one of the most confusing pieces of vocabulary is going to be this conjugate vocabulary, conjugate pair vocabulary. An acid-base reaction, a reaction where an acid reacts with a base, which is essentially any reaction, even those with water, can be viewed as an equilibrium reaction where the acid donates a hydrogen ion to the base with the reverse reaction, reversing that process. So what is a conjugate acid-base pair? When we refer to a conjugate pair in an acid-base reaction, we mean an acid-base pair on each side of the reaction, meaning one on the reactant side and one on the product side, where the two compounds are related by the difference of a hydrogen ion. That's going to give us the conjugate pair, which is going to consist of a conjugate acid and a conjugate base. So let's look at this a little better. Let's say we have the reaction of ammonia with water, which we have here. In this reaction, ammonia is acting like a base, where water is acting like an acid. The water donates a hydrogen from the water to the ammonia. The ammonia becomes ammonium, and the water becomes hydroxide ions. Well, because this is an equilibrium reaction, we can look at the reverse reaction. In the reverse reaction where ammonium reacts with hydroxide, going backwards, the reverse reaction, ammonium can donate a hydrogen to the hydroxide. In that sense, the ammonium acts like an acid, And then the hydroxide, which is picking up the hydrogen, acts like a base in the reverse reaction. So in both sides of the reaction, when it's at equilibrium, we have something acting like a base, something acting like an acid. Something acting like an acid, something acting like a base. Well, when we talk about conjugate acid-base pairs, we are talking about what the reactant and product are that are separated by hydrogen ion. So in that same reaction, ammonia, NH3, which is acting like a base in the forward reaction, when it gains the hydrogen from the water, it is becoming ammonium, which acts like an acid in the reverse reaction. So ammonia and ammonium are a conjugate acid-base pair, with ammonium being the conjugate acid and ammonia being the conjugate base. Why are these a conjugate acid-base pair? The difference between NH3 and NH4 plus is a hydrogen, an H plus. So the difference between these two things is simply just, an H plus. Ammonium is simply NH3 with an extra H plus. So that makes it the acid, and the ammonia, which does not have the H plus, is the base. The same can be true of the water, or it can be said of the water. If we look at the water here, water is losing a hydrogen, so it's acting like an acid. Well, what does that water become when it loses a hydrogen? It becomes hydroxide, which is acting like a base in the reverse reaction. So water and hydroxide are on opposite sides. One's a reactant, one's a product. The difference between them is an H plus ion. Water has the H plus, hydroxide does not. So that makes acid the conjugate, water the conjugate acid, and hydroxide the conjugate base. Water and hydroxide are a conjugate acid-base pair. All right. So conjugate acid-base pair just means when you have a neutralization reaction, acid-base reaction, it's the base on one side and the acid it becomes on the other, or vice versa. The acid on one side and the base it becomes on the other. The conjugate acid-base pair should only have a difference of an H plus ion between them. So if you remove the hydrogen from H2O, it becomes OH minus. That's the difference of one hydrogen. That's a conjugate acid-base pair. Or conjugate acid for the water, conjugate base for the hydroxide. So let's look at some questions from the AICE exam. In this question, we have a very wordy beginning to the question, but then a very simple definition. So let's read the heading for the question before we get into the definition. 25 cubic centimeters of 0.1 mole per cubic decimeter hydrochloric acid is added to a beaker and its pH is recorded. 50 cubic centimeters of 0.1 mole per cubic decimeter NH3 is added to HCl in 5 cubic centimeter portions. The pH of the mixture is monomer until the NH3 is added. HCl is a strong Brønsted-Lowry acid. So this is a setup for a mathematical question that we will see in the very last section of this chapter, 8.7. But let's focus on the part of the question that we have here, the very first part, which is a definition. Describe what is meant by a strong Brønsted-Lowry acid. Well, in this definition, you might have noticed by now in this question, we have a 2-point question, or a 2-mark question. And the question says to describe, meaning that it is not an exact definition that you learned, but it's something that you should be able to put together from what we learned. So the definition of a strong Brønsted-Lowry acid was never taught to you, not even in this video, but we discussed what it implies or what it means to have a strong acid, and we discussed what it means to have a Brønsted-Lowry acid. So what we're doing here is we're putting those definitions together, right? Brønsted-Lowry acid means that we have, and I'm going to put it in the same color. So a Brønsted-Lowry acid means that we have a proton donor. So that's the first part of the definition, a proton donor. And then the strong means that we have something, or an acid, that completely dissociates. In water. So you did not learn the definition of a strong Brønsted-Lowry acid, but you learned what Brønsted-Lowry acids are. They're proton donors, and you learned what strong means, which is completely dissociates in water. So we can put these two together because we're describing, we're not stating. Stating will be something that we directly learn. To say that a strong Brønsted-Lowry acid is an acid that is a proton donor and completely dissociates in water. If we look at the mark scheme, that's what our 2 points are for. One for stating what essentially a Brønsted-Lowry acid is, a proton donor or H+ donor. And then the second one is for stating what strong means, something that fully dissociates in aqueous solution or water or solvent. So this type of question you gotta be careful with because the number of points will give you an idea that there are 2 parts to this definition. And if we look at what it asks us to define, we can tell what those 2 parts are, the strong and the Brønsted-Lowry acid. So let's look at one more question. Oops. So, it's the exact same heading, right? So it's part of the same question. This is D2 instead of D1. But again, we're not going to use all of these math as for section 8.7. We can look at what it's asking us for. NH3 is a weak base. Okay, so that's good to know. We know that NH is a weak base. They had told us HCl is a strong acid. Construct an equation that shows the behavior of NH3 as a weak Brønsted-Lowry base when dissolved in water. So what they're asking us to do here is essentially to draw up the dissociation reaction for NH3, which is a weak base. So a few things we need to consider here. This is only 1 point question, but it's very easy to mess up if we're not paying attention to the details. So first of all, we have NH3 is our reactant. And they're asking us to construct, meaning we might not have seen it before, though we have, an equation that shows the behavior of NH3 as a weak Brønsted-Lowry base when dissolved in water, meaning that water is our other reactant. So it's important to understand here that ammonia, NH3, is acting like a base here, which means that water, which is amphoteric, is going to act like an acid, meaning that it's going to donate the hydrogen to the ammonia. So when we write our reaction, we also need to realize that this is a weak base, meaning that our reaction is not going to be a complete reaction, it's going to be an equilibrium reaction. So we have reactants that we get from the question, NH3 and water. We know that this is an equilibrium reaction because it's a weak base. They even tell us ammonia is a weak base even though they didn't need to, because we should know that. And so if ammonia is acting like a base and water is acting like an acid, hydrogen is going to transfer from the water to the ammonia. NH3 is going to create, when it receives a hydrogen, it's going to add an additional hydrogen, so it's going to be NH4. And because hydrogens have a +1 charge, it means it's going to be NH4+. NH4+ is a conjugate acid to ammonia, which is a conjugate base. And then the water, which is going to lose a hydrogen, meaning it's going from H2O to OH. Because a hydrogen leaves with a +1 charge, it's going to leave the hydroxide with a -1 charge, making OH-. So that's our construction. We get the reactants from the question, NH3 in water. From that, because they tell us that the NH3 is acting like a weak base, we know water is amphoteric. We should know that water is acting like an acid. Because it's weak, we know that it's an equilibrium arrow. If it was strong, it would be a complete arrow, but it's an equilibrium arrow because it's weak. And then we know that NH4+ is going to be created from the ammonia acting like a base, bringing in the hydrogen plus, so extra hydrogen +1. And then the acid, the water, is going to lose a hydrogen, so H2O becomes OH, -1 hydrogen. And then the -1 charge because it lost a +1 charge in the hydrogen. And so that's our reaction. This is really a reaction that you should have memorized, but even if you didn't, you should be able to use this knowledge to put it together. So those are just some basic theory questions that you might be asked. I would ask them basis. We will in 8.7 look at how to more clearly look at the mathematics that go along with these, although they are pretty standard titration mathematics. So we'll look at those in 8.7 along with the graphing of these titrations. But for now, that's it for section 8.6. I'll see you all in the next video.